Good day to all the distinguished members of the organizing committee, respected reviewers, and the attendees of the 10th IEEE International Conference on Automatic Control and Intelligent Systems. I am Dr. Mihir Mehta and I am honored and privileged to present our collaborative research entitled Enhanced Maximum Power Point Tracking Performance in Solar PV Systems using ANN and FOPI controlled optimized by metaheuristic algorithms. The structure of this presentation is systematically designed. It begins with a comprehensive literature survey followed by the statement of our research objectives, a detailed overview of the proposed system architecture, and the mathematical model foundation of the optimization algorithms. We will then walk through our simulation setup and the experimental results, concluding with the key observations and contributions. The increasing demand for clean decentralized energy has thrust solar PV systems to the forefront of the global energy production. Their eco-friendly footprint and direct sunlight to energy conversion render them high desirable for both grid-connected and standalone applications. Yet, PV system remains inherently nonlinear, highly sensitive to environmental conditions such as irradiance and temperature. Effective grid integration thus mandates robust control strategies, most notably for maximum power point tracking, voltage stability, frequency control, and reactive power management. On the other hand, solar PV systems are ideal for remote areas due to low demand, minimal maintenance, and cost effective operations. Although PV systems operate at lower efficiencies between 6 to 20%, make them vulnerable to even minor atmospheric fluctuations. These perturbations can induce rapid and irregular shift in the peak power points, affecting both energy output and system stability. Modern MPPT techniques have evolved rapidly, focusing on improved tracking accuracy and reduced convergence time. Nevertheless, challenges persist, especially when confronted with weak grid conditions, impedance mismatch, and dynamic load disturbances. Traditional implementing methods such as P&O, INC, and open circuit methods suffer limited adequacy under real-time dynamics. Even variable step size techniques have proven inadequate in highly volatile scenarios like partial shading. This has led to emergence of intelligent algorithms including artificial neural network, ANFIS, and others. While promising, these methods still require enhancement in terms of speed, robustness, and control granularity, particularly under fast changing environments. In light of the identified research gaps, our study is guided by the following four objectives. To design an ANN-based MPPT algorithm capable of generating an optimal reference voltage with high precision under variable solar irradiance. To implement fractional order PI controllers known for its superior dynamic response compared to classic PI controllers. To optimize the gains of FOPI controllers using two metaheuristic algorithms, that is the Gray-Wolf optimization and the Flower Pollination optimization. And lastly, to achieve consistent and enhanced power extraction from PV systems under real-time operational conditions. Our proposed control strategy is a multi-layered hybrid control framework. The ANN block receives environmental input like solar irradiance and temperature and predicts the ideal reference voltage for MPPT. This predicted value is compared against the actual PV terminal voltage to generate error signal. This error signal is processed by FOPI controllers whose unique capability to handle nonlinearity via fractional integral term enhances both tracking accuracy and system responsiveness. The use of conventional PA controllers is compared with FOPI controllers, which are tuned by two metaheuristic algorithms, FPA and GWO. FOPI controller tries to mitigate the errors using the given formula. Thus, the test system architecture combines intelligent prediction, fractional order control, and nature-aspired optimization, making it highly adaptable to complex real-world energy scenarios. The mathematical foundation of Flower Pollination Algorithm reflects a balance between exploration and exploitation. Global pollination is modeled via levee flights. Shown in the equations, xit denotes the position of the vector of ith solution at the iteration t. X star represents the global best solution identified so far. Alpha is a scaling parameter controlling the step size, and S denotes the step drawn from Levy flight distribution. Local pollination emphasizes fine tuning near high performance solutions. In the equations used, xjt and xkt are two randomly selected solution vectors, and beta is random number uniformly sampled between 0 and 1. This mechanism primarily enables local exploitation around promising regions. A probabilistic decision governs the selection between global and local pollination based on the switch probability parameters PS. Pseudocodes provide a transparent step-by-step flow of algorithms. This is particularly useful for early-stage researchers and engineers, allowing them to grasp logic and implementation nuances without diving into complexity of mathematics. Such structured representation not only democratizes understanding but also fosters reproducibility in future studies. The mathematical foundation of grey wolf optimization reflects a balance between exploration and exploitation, draws inspiration from hierarchical hunting strategy of wolves in nature. The three base solution X, alpha, beta, and delta guide the optimization process, while the remaining population, that is the omega wolves, follow the leaders. A and C are the coefficient vectors. XP represents the prey position, X denotes the current position of the vector, R1 and R2 being vectors of random numbers uniformly distributed between 0 to 1, and A is linearly decreasing parameter from 2 to 0 over the course of iterations. Since the exact position of the prey is unknown, the governing equations simulate encircling the prey and iteratively adjusting the position converging towards the optimal solution. The wolf updates its position according to the position of x, alpha, beta, and delta. Coefficients A1, A2, A3, and C1, C2, C3 are generated independently per leader per iteration. Final update is the average influence of the top three leaders. Through this mechanism, GWO simultaneously exploits the best solution found and explores the surrounding search space, leading to a well-balanced optimization process. The pseudocode clearly illustrates the sequence from coefficient initialization to fitness evaluation and adaptive convergence, enabling intuitive comprehension for researchers unfamiliar with bio-inspired computation. The test system is implemented in MATLAB Simulink using 248.9 watt PV module, and a DC-DC boost converter is used to regulate the output voltage. The details of the numerical parameters are shared to foster reproducibility for future research use. We examine both the PV and the IV characteristics under varying conditions, which reveal how the system transitions from suboptimal to peak power points. These fundamental plots validate the fidelity of the system model and the responsiveness of the control logic. Real-time irradiation variation from 0 to 1000 watts per meter square is plotted to reflect the performance under fluctuating sunlight, which is a key requirement for intelligent MPPT systems. The figure represents the basic block diagram of an ANN model, and the table represents the ANN model's training performance. With 7,000 training samples, 1,500 validation samples, and 1,500 testing samples, the model achieved exceptionally low mean square error and near perfect regression values across all database, confirming excellent accuracy, generalization, and consistency in reference voltage prediction for MPPT. This figure shows the ANN model's training performance, where the mean square error converges rapidly to 9.95 into 10 raised to minus 11 at 1000th iteration, indicating excellent learning and generalization, whereas the error histogram shows the most prediction errors are tightly clustered around 0 for training, validation, and testing datasets, further confirming the model's high accuracy and consistency across all partitions. The table compares the optimized gains of PI and FOPI controllers. The PI controller is tuned by MATLAB's autotuner block, and FOPI controllers are tuned by FPA and GWO algorithms. Figure illustrates the analysis of the performance of the three controllers with respect to the power delivered during variable solar irradiance conditions. The conventional PI controller exhibits a significant delay in responding to the changes in the irradiance. The power delivery curve shows a sluggish rise, especially noticeable in the initial few seconds. Moreover, the system experiences marked overshoot between 5 to 6 seconds and undershoot visible at both 7 and 9 seconds, indicating poor adaptability and suboptimal dynamic response. Moving to GWO tuned FOPI controllers, we observe a sustainable improvement. The rise time is faster and the tracking of irradiance variation is far more accurate and stable. While minor overshoots are still present around 7 and 9 seconds, their magnitude is considerably reduced. This improvement clearly demonstrates the impact of using Gray Wolf Optimizer for gain tuning in enhancing the overall system responsiveness and efficiency. The most impressive performance is seen with FPA tuned FOPI controllers. This method delivers fastest and most accurate tracking of irradiance profile. It exhibits minimum overshoot, rapid stabilization, and maintains a near perfect alignment between the power output and the irradiance input throughout. This indicates superior robustness, dynamic stability, and control efficiency. Among the three control strategies, the FPA tuned FOPA controller outperforms the other two, offering optimal real time power tracking capabilities under dynamic solar conditions. The primary graph illustrates the tracking error over time, where the FPA tuned FOPA controller exhibits lowest and most stable errors, followed by GWO tuned FOPI controller, while the tuned PI controller shows significant overshoots and undershoots. The second graph compares the integral square error values, where FPA achieves the lowest ISC value of 1607.73, outperforming GWO and PI, indicating superior precision and dynamic performance. Agglomerating the points discussed so far, our proposed system achieves a synergetic integration of ANN-based prediction, FOPI control, and the metaheuristic optimization. Amongst the two algorithms, FPA-tuned FOPI controller demonstrates superior results across all platform matrices. This hybrid architecture ensures higher power extraction, minimal steady-state error, and robust dynamic performance. The artificial neural network, combined with FPA-tuned FOPI controller configuration, is ideally suited for real-time converter control in next-generation PV installations. I will briefly skim through the references that underpin the technical and algorithmic foundation for this research work. On behalf of my co-authors, I extend our heartfelt gratitude to the organizers of I2CSCIS 2025 for providing us with the esteemed platform to share our research and engage in global discourse on intelligent renewable energy systems. We deeply appreciate the time, attention, and interest shown by the distinguished audience. Your presence encourages continuous innovation and collaboration in this vital field. Thank you.